Okay, thanks a lot to Rajiv and to this conference organizers for having invited me in such an interesting event, which has also this online precursor due to the terrible COVID emergency. So I have organized my talk with a brief introduction, some highlights of Planck 2018 result for inflation, and some perspective for future observations. So in summarizing the observational status of inflation, CMB anisotropy pattern has the lion's share of the constraining power. Thanks to the different imprints of scalar and tensor perturbation, temperature and polarization of the CMB anisotropy pattern, we can constrain power spectra of scalar and tensor perturbation and the statistics. So to make contact with what Nicola has already said, by constraining the scalar and tensor power spectrum, you can constrain the inflationary parameters, either the Hubble rate during inflation and its deviation from an exact exponential expansion, or the inflationary potential. And here I'm just reporting as a reference the theoretical inflationary slow-roll prediction of the primordial power spectrum to second order in slow-roll parameter for the simplest models. In an historical perspective, it is interesting to visualize how the better and better measurement of CMB anisotropies to finer angular resolution was of key importance for the constraints on inflation. So this plot shows the state of the art of measurements of CMB temperature power spectrum approximately 20 years ago. And this has evolved, and the milestone is the Planck 2018 power spectrum, the third data release, in which not only the temperature power spectrum are present, but also polarization, temperature polarization cross-correlation, and lensing power spectrum. So for each panel, are reported also the residual of the data with respect to the best fit of Planck data in temperature, polarization, and lensing for the lambda CDM model. This improvement in measurement carried a better understanding of cosmology and inflation. So in this figure, you see reported the evolution in time of the measurement of cosmological parameters and main primordial parameters from a pre-WMAP era to the Planck 2018 release, and the visual impression of improvement in the uncertainty for this parameter is obviously impressive. So also in this talk, I will focus on Planck results with a few important additions. Planck is very consistent with other measurements, which can constrain primordial fluctuation. So in the left panels, Planck is consistent with WMAP in the range of high signal to noise for both explaining for WMAP, and is consistent with temperature, polarization, and CMB lensing measurement from ground experiments as SPT pole, ACT pole, which extend to higher multiples. Planck is also consistent with galaxy surveys at redshift 1, more or less. Either the baryonic acoustic oscillation scale distance and the matter power spectrum agree with the Planck corresponding inferences for this quantity. And last but not least, measurements of B-mode polarization from BICEP to Keck array in combination with Planck and WMAP can further tighten the constraints on primordial gravitational waves, which Planck sets mainly thanks to temperature and E-mode polarization due to the poorer noise sensitivity compared to the BICEP and Keck array instrument. So let me now discuss the Planck scorecard for inflation. So Planck is consistent with the key prediction of the simplest inflationary model And by simplest, I mean the slow roll single field with a standard kinetic term, Bunch-Davis initial condition on a flat Friedman-Robertson-Walker metric. So as already mentioned by Nicola, we have a measurement of consistent with a flat universe at the percent level by Planck and below the percent level with the combination of baryon acoustic oscillations. There are deviation from scale invariant for the spectrum of curvature perturbation detected at more than 8 sigma. This is the most precise measurement of the scalar spectral index, which has no statistical evidence of any scale dependence, and therefore the running is consistent with 0. So as Nicola already mentioned, the perturbation, the statistics of perturbation is consistent with a Gaussian one, and I'm reporting here the bispectral parameter for the main local, equilateral, and orthogonal shapes. So there is no need for additional fields during inflation. We have an important test for adiabatic fluctuation, which translate in upper bounds. And I'm quoting here the result for CDM isocurvature fluctuation on upper bounds for uncorrelated fluctuation, as in the case of axion, at the few percent level, or even below at the 1 per mil level for the curvaton, for fully correlated isocurvature perturbation. So in the previous Planck release in 2015, we also constrain the contribution from active sources, and in particular from strings, from cosmic strings. I'm quoting here as a 2% the 2 sigma upper bound for the contribution at multiple 10 of the cosmic strings with respect to the adiabatic mode for Nambu-Goto case. So data are also compatible with a small relative amount of gravitational waves, as I show the R, the tensor to scalar ratio for simplest model is proportional to the first slow roll parameter. We have a limit at 2 sigma of 0.1 from Planck data alone, which can be further tightened with the combination of bicep and Keck array 15-year data to 0.056, which translates in an upper bound on the energy scale of inflation of 1.6 in 10^16 JeV. So these results are obtained by assuming the relation between the tensor tilt and R supported by standard slow roll single field inflation. If you relax this assumption, then we have analyzed the data with a 2-scale analysis as for isocurvature perturbation, and then we find a limit on R and a derived marginalized posterior for NT, which includes the tensor, the relation of the tensor tilt and R for the simplest model, and also allow larger phenomenological value of NT as order of 2. So by folding limits on gravitational waves at 20 years, scales much smaller than the CMB probe, the CMB one, by folding in this limit from LIGO and Virgo 2016 data, they allow marginalized derived 2 sigma range for N3 shrinks between -0.8 and 0.6, always including the standard slow roll relation for NT. So given this scorecard for the most important result for inflation, let's go to a little bit in detail, in particular for the simplest model of inflation, since these are consistent with the data. It's interesting to illustrate with the joint NS-R plane in which are depicted the 68 and 95% confidence level contours. Planck data are in gray, and in combination with BK15 in red. You can see that the red contours, the 95 confidence level red contours, are entirely in the region of the concave potential. And at some point, there could be a strong preference for these models. And in blue, the contours are obtained with the further addition of baryonic acoustic oscillation compilation of data, which show how the NS is just shift to a bit to the right, to higher value, but the uncertainty are approximately the same. In addition to the data contours, there are some prediction for inflationary model with the associated uncertainty in the post-inflationary era, taken usually as a range in the number of equals to the end of inflation between 50 and 60. We can see that the family of monomial potential grays the 2 sigma data contours, and from the opposite side in purple, there is the corresponding strip for natural inflation. The quartic hilltop model is inside the data for most of the parameter space, and at the center of the data, the Starobinsky model sits with a very small tensor to scalar ratio, roughly 4 × 10⁻³ which cannot be probed by Planck. So there's the yellow line, the T alpha tractor models introduced by Kallosh and Linde, which interpolates between the R-square model and the quadratic potential, which is now firmly ruled out by the data. So to complement the visual impression of the NSR plane more rigorously at a statistically significant level, we have performed a comparison of theoretical prediction to second order in slow roll parameters of a selection of representative simplest inflationary model with Planck data. So we have considered uncertainty in the post-inflationary stage by allowing to vary the energy at which the universe thermalizes, and the average equation of state during the thermalization process, as also done by Jerome Martin and collaborators. And this quantity are the microscopic physical quantity which enters in the relation with the number of equal to the end of inflation, which relates basically the scales during inflation to the scales with which we analyze the data at present. So in this way, we have quantified how monomial potential, natural inflation, and potential including logarithmic correction are now strongly disfavored by Planck 2018 and BK15 data, while another models as R-square, D-brane inflation, alpha tractors, potential with exponential tails provide a similar fit to Planck and BK15 data. Another important question we have addressed is if inflation was driven by more than one field. Detecting isocurvature perturbation would indicate a multi-field dynamics during inflation, since the isoperturbation generate would have left then a component in the radiation-dominated universe after Big Bang nucleosynthesis. And the prediction of inflation also is, in general, that this fluctuation can be correlated with curvature fluctuation. So we can classify isocurvature mode as a regular growing non-constant as the curvature one, modes for curvature perturbation. In this way, in the standard lambda CDM, you have an isocurvature mode for matter and 2 isocurvature in the neutrino sector, one for density and one for velocity. And CMB is the primary observer to constrain isocurvature, thanks to the different transfer function in temperature and polarization. We already know from WMAP first year data release that only a fraction of isocurvature can be present, which means that isocurvature alone cannot seed structure formation as we observe. So Planck polarization provided a very stringent test for adiabatic initial conditions. So any model including isocurvature perturbation for CDM, neutrino density or neutrino velocity with 1 or 3 extra parameters are now strongly disfavored with respect to the adiabatic initial condition. So with the precision of Planck data, let me also stress that the addition of one of these isocurvature mode does not lead to a substantial degradation in the certainty of the other cosmological parameters. Let me now have a small digression on how there could be additional isocurvature mode in general. So as for the adiabatic case, one could consider extension of lambda CDM with these linear isomodes. There could be, as studied in the last Planck paper, could be studied the baryon CDM mode, which leads to a smoothing of the acoustic peaks similar to a lens. Or there might be other isomodes, other isocurvature solution when additional dynamics degrees of freedom are present as in extension of lambda CDM. So as an example of this, we have identified the isomode for the simplest scalar tensor model, the extended Jordan-Brans-Dicke theory, which is really the workhorse to study the extension of general relativity. And this is a new isomode which can be identified and can be studied its effect on the CMB temperature and power spectrum, finding that there are differences with respect to the adiabatic mode in this theory at multiple smaller than, let's say, 100, 200. So in this case, because these are relegated to low and intermediate multiple, when you put constraints on the fraction of this isocurvature mode, you find in general bounds which are relaxed with respect to the standard mode in lambda CDM. Another question which we address is if there is evidence for feature in the primordial power spectrum, or better, if the departure from the lambda CDM best fit the outliers of data with respect to the lambda CDM best fit call for new physics beyond the inflationary models, as an example, a violation of slow roll. And this is also connected with Diray's talk, which follow. I'm restricting here to give just one result from the Planck papers. So we have updated the search for feature in the latest Planck release by considering theoretically motivated templates, which belongs to two broad classes: local ones, which aims in fitting outliers at multiple less than 40, and global model, which have oscillation on all the range of wavelengths probed by Planck. And the result, very short, is that with analysis of temperature alone, polarization alone, or jointly in temperature and polarization, we don't have any preference with respect to a simple power law power spectrum for these local or global models, even if the delta chi-square, there is an improvement due to the additional parameters. And the results are also corroborated by complementary primordial power spectral reconstruction, which do not use a particular form of theoretical templates. So let me turn now to the to some perspective for future observations, the post-Planck effort in improving CMB anisotropy measurement at all angular scales will continue in the next decade, with ground, suborbital, and space experiments in preparation. So this list could be incomplete eventually. And the science case for this new experiment or new concepts have been properly spelled in several publications. And one of the main drivers for future CMB experiment is obviously the search of B-mode polarization from gravitational waves. And the natural question is how the uncertainty in the tensor to scalar ratio or in the NSR plot will evolve in a decade. And I'm considering here a couple of examples. The uncertainty on R will improve by approximately an order of magnitude with respect to the current VK15 and Planck limit, as in the case of the Simons Observatory, which is a ground experiment in Chile. On a longer timescale, LightBird, a space project led by JAXA and with the contribution of North America and Europe, will probe both reionization and recombination peaks of inflationary gravitational wave, reaching an uncertainty of 10 at -3, including margins, which should allow a statistically significant detection of the Starobinsky model, which, as we saw, is the first and simplest complete inflationary model proposed and among the preferred models by Planck. Okay, let me leave to explain how this noise sensitivity of future experiment can be important also for the E-modes and in particular for features. And let me describe instead another aspect, how the stage 4 galaxy surveys in operation or preparation, whose main scientific driver was actually dark energy and dark matter, could also contribute to improve the current inflation constraint based on Planck. So we will have an increased level arm to smaller scale, which will lead to tighter constraints for NS and its running. But here, instead, I would like to give a snapshot of the complementarity between CMB and future galaxy survey for non-standard deviation of the primordial power spectrum from a power law, as in the case of feature. So we first consider different spectroscopic surveys as DESI, Euclid, and SPHERIX, and consider models which are actually hidden in the Planck data in terms of size of the parameters. So we found that by just considering conservatively linear scale, already these galaxy survey are very complementary with CMB for many models, and including potential with a step. And instead, for global models as logarithmic oscillation, as predicted from instance from axiomonodromy or non-initial condition different from Vance-Davis, then you can actually detect these with a combination of current CMB data and, for instance, Euclid. If one considers the next generation of photometric or radio surveys, which actually probe a larger redshift volume, then these surveys could be even relevant for the local model, which aims in explaining such large features at very large scales as L equal 20. But then the next question is, how can the cosmological information contained in galaxy survey can be fully explored in the context of feature, in particular those global models with extend feature to very small scales probed by galaxy surveys. For these models, commonly used methods as halofit are not suitable, and a dedicated study is needed. So perturbative nonlinear analytic methods or embodied simulation show in a consistent way an attenuation of this feature at small scale, which is an effect which becomes more and more relevant at lower redshift. So this nonlinear damping can be modeled by mutuating the physics from baryonic acoustic oscillation with a exponential damping, which has also a perturbative formula from perturbation theory. So this attenuation becomes important for publicly available data, and we see here the constraints from Bettler et al. Using Planck 2015 data and Boss DR12 data. And this can be used also for forecast. And here you see forecast for Euclid data and Planck 2018 simulated data, which shows basically two things. First, that including nonlinear scales is important to show how these galaxy surveys could be competitive with the current CMB measurement in constraining the amplitude at the same level. And at the same time, because of this exponential damping, for this case of linear oscillation, you can actually arrive to a maximum wavelength of the order of 0.6, close to those obtained by non-perturbative analytic method in order to get all the constraints from galaxy surveys. So let me just show another couple of slides, concluding that we have concentrated on CMB and less scale structure constraint on the primordial power spectrum, which cover 4 decades in wavelength, and while other smaller scales are really inaccessible or poorly constrained from other probes. So here I'd like to stress that there are models with enhanced small scale power as work by Subodh, which actually could be immediately ruled out by having experiments which probe spectral distortion to a very ambitious level, as proposed by Pixie, or experiment which goes beyond Pixie for Voyage 2050. And there could be also effect at small scale in gravitational ways, depending on the model, if this feature at smaller scale as worked out by Matteo Braglia and also in collaboration with Sriram and Viraj, which there could be effect also on the gravitational waves at small scale probed by interferometers, as discussed by Nicole. Okay, let me conclude. Planck is currently the most decisive dataset for inflation and is consistent with key prediction of the simplest inflationary models, standard single field slow roll models, puts tight constraint on strong departure from a nearly power law primordial power spectrum, as a curvature perturbation, primordial non-Gaussianity. And because of cosmic variance and the Planck noise in polarization, we didn't find any compelling theoretical interpretation in terms of new early universe physics, prefer over these simplest models of inflation. For the intriguing and long-standing problems as outliers in the temperature power spectrum at low L or high multiples. However, forthcoming E-mode polarization will be relevant for this. And the improved measurement of B modes promise to constrain inflation, giving either a detection or an upper limit on R. So galaxy surveying operation or implementation are really complementary to CMB, either providing independent measurement at the same scales or extending the leveler towards smaller scale. And I gave an example of how it's important to model nonlinear scale for studying these models. And obviously, We have just discussed the traditional CMB large-scale structure range of wavelengths, but there are other observable as CMB spectral distortion, small-scale gravitational wave, which can be probed by interferometer, which could open new important windows. And let me thank for your attention.
Thank you very much, Fabio. So as I requested you, I will request you to be available after Dheeraj's talk in this discussion session, and we will take up all the questions which are for your talk as well as for Dheeraj's talk after Dheeraj's talk. Okay, so kindly be available.
Okay, sure.
Yeah, thank you. Thank you, Fabio, once again.